I wanted to make a quick video about the fact that there are higher order Bessey sequences. In fact, technically there's an infinite number of them, but they are actually rare, as we'll see. So the claim here is that there is a complementary pair of Bessey sequences for each packet size of 2 to the n for n odd. Okay, so that would be a packet size of 2, 8, 32, 128, and so forth. Okay, so in this video, I'll show you a quick example of that, and then I also want to show you how I constructed these Bessey sequences. So I have here a packet of 32 cards, and I could give you as long as you would like to kind of study this packet, and it's highly likely that an ordinary observer would never find any structure or pattern to this packet of cards. You could have them look at it for a long, long time. Okay, so the claim is this is a Bessey sequence of length 32, which it is. So being a Bessey sequence, what that will mean, as we'll see moving forward, is that any of the shuffles that we used in this series where we've been working with Bessey sequences of length 8, any of those shuffles will preserve this structure or possibly convert it to its inversion. Inversion just means the zeros and ones get switched. Or if we're focused on red and black cards, the red and black cards switch places. That's what the inversion is, okay? So why don't we just quickly go through and do some mixing here. So LR shuffle. Now with random stacking decided by the spectator, that's the important thing. Okay, so they can decide left on right or right on left. Maybe they want left on right. That's just fine. Now, because of the stay stack principle, technically we have far more options for mixing this packet of size 32 than we would for a packet of size 8. And that's for the simple reason that 32 has more divisors than 8 does. So in particular, what that means, of course, is that we can deal into 4 piles. And this is something we could do with a packet of size 8, because 8 is divisible by 4. Okay. And now we're free to stack from left to right or right to left. We can even do the leapfrog stacking. So that still holds in this higher order case. Okay. Now, because 32 has a divisor of 8, we can actually deal into 8 piles if we would like. Not sure why I'm not centering those. I apologize for that. So we can actually deal into 8 piles like this. And then we could stack, quote, from left to right or right to left. Okay, so maybe the person wants to go right to left. That's just fine. We could even do a leapfrog if that was asked for. Now, something I haven't, let me just drop those on top. Something I haven't actually been using much, and it would work really well here, is with this dealing out that we're doing into multiple piles. So in the case of 4 piles, we don't necessarily have to go left to right. You can actually deal down. You can go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You can actually deal down. It doesn't necessarily have to be for across, okay? And I'm doing a leapfrog stacking there and making a complete mess of things. Okay, so that's some of the LR or the multiple pile stacking and dealing. We can do even or odd up jogs. You can do as many of these as the spectator calls for, and they can decide, okay, should we stack the left on top of the right or the right on top of the left once we strip these out? Okay, so there we go. So we'll strip out. These are the even position cards. Which one do you want this one on top? That's just fine. We can actually do a mange, over, under, or under, over. And we can do as many of those as you like, or the spectator likes. Dropping the cards there. There's so many of them. Okay, so any form of mange, you can do a Klondike. And once again, you can do as many of these as you like. This is where you take the top and bottom card off as 1. And I've mentioned that this particular shuffle has quite a fun etymology, a history behind the name of the shuffle that you might want to look up. Okay, and so that's a Klondike. The Australian shuffle, this is where you go down, under, down, under, down, under. It would work for this as well. It might take a little too long here just because of how many cards, but you can try that on your own. That's where you go down. Next one goes under, down. You can do a 50% coating. That's where you just deal out half the cards, drop the rest on top. You can do a Charlier 1. If you remember, that's where you push one card over and the bottom to top, top to bottom, bottom to top, top to bottom. Okay. So you do that until all of the cards have been moved from one hand to the other. Okay, so this is a top to bottom sort of dealing. Now, it is true that we're moving just one card at a time. That's why it's called the Charlier 1 and not a general Charlier shuffle. Okay, that's a little different. Okay, we can do a Bessey 1-1 or a Bessey 2-2, actually. 1-1 is where you take the top and then the bottom, top, bottom, top, bottom. I want to point out that this is different than it might seem similar to the Klondike. In some ways it is similar, but it gives you a very different ordering of the cards. So that's important to be aware of. Sometimes shuffles will seem similar, but not identical. And so they give you a different ordering. We can also do a Bessey 2-2, and that's a fun one as well. This is where you take top 2, 1, 2, and then 2 from the bottom, 2 from the top, 2 from the bottom, 2 from the top, 2 from the bottom. And you do this until all of the cards, of course, have been moved from one hand to the other. And you're just doing 2 from the top, 2 from the bottom, 2 from the top, 2 from the bottom, 2 from the top, 2 from the bottom. Okay. We can do an alternate Klondike. In fact, here you can put it out into multiple piles if you want. So we could just do 2 piles. That would be just fine. Or you can actually put it out into any number of piles that divides into the 32, which is the packet size here. Okay. Now we can do a stacking from left to right, right to left. We can do a leapfrog if you would like. This is where you jump over the neighbor with random stacking here. That's just fine. We could do a pharaoh. That one's going to be a little fussier. That's where you perfectly interlace them. We can do an LR inverse. We can push off pairs. We can do that as well. Not sure how many of these we should actually do. Let's see. How about if we do a repeat LR? That's kind of a fun one. So this is where you go left, right, left, right. Now I want you to think about all of the mixing that's going on. Okay. Whoop, sorry about that. All of the mixing that's going on here. Okay, and we're not going to stack them this time. This is the repeat. So what that means is you do LR once, and then you do an LR again, and you can do as many LRs as you like, actually. Oh, I'm doing it the faster way here, if that's okay. Just, I'm doing left, right. It's just kind of a faster way of creating the piles. Maybe I'll just do it traditional here so I don't kind of throw people off. Okay, and now we could go through if we wanted to, and I want to point out something fun right here. Each of these is a Bessey sequence of length 8. Can you see that? We have black, red, red, black, red, black, black, red. I want to point that out to you. These are all little baby. Talk about fractals, a fractal relationship here. Red, black, black, red. black, red, red, black. Okay, so if you've been watching the series on Bessey sequences, you'll recognize that these are all individually Bessey sequences. So everything that we have done in this series could now be applied to these 4 piles individually. If I can speak here, individually. Isn't that amazing? Look at that. That's a Bessey sequence of length 8. Okay. Now these can be stacked from left to right or right to left or leapfrog. Let's do a leapfrog. And also we could have actually continued doing a left-right for each of those 4 piles, which it would give 8. And then you could stack those 8 piles left to right, right to left, or leapfrog fashion. That would be just fine. I don't know. That's probably enough. We have a number of ways of mixing the cards where we're flipping half of them. We have a folding procedure, which is kind of cool. And this is just a partial list of the ones that preserve Bessey sequences of length 8. But anything that holds a Bessey sequence of length 8 fixed or undisturbed or converts it to its inversion will also work for a Bessey sequence of length 32, okay? Now, I do want to point out, let me go back here. Now, there is a reason, and in fact, I want to explain this in just a second. You need to have an odd power of 2, okay, for this structure to technically be a Bessey sequence. So in that sense, it truly is rare, even though there's infinitely many odd powers of 2, right? In some sense, it's still relatively rare, right? So there's only 2 of length 8. There's only 2 of length 32. There's only 2 of length 128, and so forth, okay? And they come in complementary pairs, as mentioned. Okay. Well, let me just show you something kind of fun that you can do with this. Now that we've mixed it thoroughly, we can go ahead and just kind of okay, sorry, I'm kind of doing it fast. We can divide it into 2 halves. Now, we could have actually just cut off the top 16 cards, or we can do a left-right. It doesn't matter. The structure is virtually indestructible, okay? And so what we can do here is I can take these now, and I'm going to use my intuition to kind of separate the cards here. So I'm going to try to concentrate here. So, I'll put those there and those there. And that one there. And this one here. And those there. Okay, let me pick these up. That's okay. See, I think I'll put these here. Those there and those there. And then maybe over here now. And maybe we'll do another one here. And the one over here. Boy, I sure hope I used my intuition well. Let's just see how I did. How did I do? Did it work out well? Oh, wow, look at that. Those are all black. What are these? These are all red. Has your head exploded yet? Okay, so anyway, that's just a simple application of the fact that we are preserving this structure where key choices are being made by the spectator. That's the important thing. So I just want to step through kind of how I constructed these Bessey sequences and why it is that it's only odd powers of 2 that give rise to what I call Bessey sequences. These are the ones that are preserved by way of this whole list of systematic mixing procedures that are commonly used today. Okay, so let me see if I can explain this here. Okay, so it's a iterative thing, so we're going to kind of build packets of larger and larger size. Now, in some sense, this is the degenerate case. It's not going to be interesting, but so if we have a sub 0 be equal to 1, and a sub 0, now the bar, as mentioned here, it just means the inversion of this, of whatever sequence makes up a naught here. Its inversion is where you switch zeros for ones and ones for zeros. That's all that means, okay? So if we start here and now use this pair as a way to build a larger sequence, this will be the construction that leads to Bessey sequences. Now, it's the same sort of construction that leads to the thue-morse sequence. Now, in that case, the sequence begins with a 0 followed by a 1. So they would have a 0 here and then assign that to be 1. But this is truly how I constructed Bessey sequences, because if you haven't read some of my write-ups, I was not even aware of the existence of the thue-morse sequence when I discovered Bessey sequences. I had no idea what it was, how it was constructed. It was only after I did my work on Bessey sequences, somebody pointed out, boy, that looks a lot like the thue-morse sequence, which is technically, it's an infinite sequence, actually. But these Bessey sequences seem to be special sections of that infinite sequence. Okay, so in my construction, I started with a 1. Okay, I wanted that as a leading digit. Okay, now to build a larger sequence with 2 elements in it, not just 1, what you do is you concatenate these 2. Concatenate just means put them next to each other. And technically, this can be mathematically defined as a sequence, okay, as a function from the set of natural numbers 1, 2 to the set with 0 and 1 in it, where the natural number 1 is assigned to the whatever's in the first position, and the natural number 2 is assigned to whatever's in the second position. Once you have this sequence of length 2, we can now build a sequence of length 4 by the same process. So what you do is A sub 1 is this sequence here. Its inversion, of course, is 0, 1. That's where the 1s and 0s switch places. Okay. Now, if you take these 2 and concatenate them, you'll get a longer sequence. And so the same thing over here. Now we just switch the order of these sequences of length 2 to get the inversion of this one. Okay. Now, it's only at this point right here when you take these 2 smaller sequences of length 4 and concatenate them, put them together, that we now arrive at a Bessey sequence of length 8. So this is the standard Bessey sequence that we've been working with throughout this whole series, and this is its inversion, okay? And if you notice, the subscript here is odd, okay? So that's important. And this has length 2 to the third. 2 to the third is 8, okay? So that is the Bessey sequence that we've been using all of this time. Okay, now if we continue this construction, what will happen for a sequence of length 16, we will take the ordinary Bessey sequence, there it is, and then we will concatenate it with its inversion. That's all we're doing. You're always taking the previous sequence and you concatenate it, which just means put them next to each other with its inversion, okay? And then here is the inversion of that one. But notice that the subscript is 4, and I'm going to make mention about what kind of structure does this have, and is it preserved by all of these different shuffles? And the answer is no, it's not preserved by all of them, by any means, okay? And that's why this is not called a Bessey sequence. It doesn't have the invariance that a true Bessey sequence does. So here, when we arrive at A5, so what we do is we take this sequence and its inversion, and we concatenate them, put them next to each other. That's all we've done. Now, I've been drawing this black bar that just aids the eye in seeing where the middle is, so you can kind of see how the parts are being put together. And here's the inversion of this one, okay? So 1s and 0s have switched places. So the claim is that this is a Bessey sequence. And this is the structure. If you go back, rewind the video, and look at the color distribution of the cards, you'll discover that it's set up in exactly this way, okay? And it's not that hard to actually see how this is built, because here's a Bessey sequence, the kind of standard one. Now you shift over, here it's inversion. Okay, so that makes up half of it. Okay, now the other half is just the inversion of this whole thing. So everywhere where you see a 1, you put a 0. Where you see a 0, you put a 1. So there you get the other half. Okay, and so this wonderful sequence of length 32 is preserved by way of all of the shuffles that I've shown you in this series, plus additional ones, of course. But the ones I've shown you will preserve this, okay? And because this has a longer length and more divisors, it gives you many, many more ways to, quote, shuffle such a packet and preserve this structure or convert it into its inversion, okay? So here is the Bessey sequence of length 32 that I was using. Now, let's talk about quickly, so what is it about the even powers for 2 raised to an even power versus 2 raised to an odd power? What's fundamentally different about these sequences that have been constructed in the way that we're constructing them here? So what is the fundamental difference? Okay, well, let's look at it here. Okay, so the claim is that for an even exponent, so here we're looking at 2 to the second, 2 to the fourth, 2 to the sixth. So why don't we focus on 2 to the fourth? 2 to the fourth is 16, so we're looking at this sequence right here. Now, I am assuming that you've studied a little bit of what's in my online course dealing with what are called CMA structures, okay? But if not, I think I can get you to understand the basics right now. Okay, so what is an OSO? Okay, well, first off, you have to kind of focus your attention on the fact. So C is for 2-cycle, M is for mirrored, this A is for AMP, okay? So in this particular example here, I claim that this is a 2-cycle relative to the opposite value. O is for opposite, S is for same, okay? A 2-cycle is where you look at the first positions in each half, and we're looking at, okay, is that 1 and the 0 right here, are they the same value or opposites? Well, they're of opposite value. Now, as you shift over 1, you'll get the same thing. Opposite value, opposite, 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 all the way down. Okay, so this is a, quote, 2-cycle relative to opposite value. Now, the middle letter here, S is for same. It refers to the mirrored structure. Well, mirrored is where you look on either end, and you compare the outer ones, and then you just come in 1. Those are both 0s. You come in 1 again. Those are both 0s. These are both 1s. So essentially, it's just saying that this is the mirror image of itself. And you can see that with the black line. And then the last one is an AMP construction. And what we do there is we're taking them in pairs. So you're looking at these in pairs from left to right. And you're asking the question, are these of the same value or opposite values as we do this? Well, as you can see, we will always have digits of opposite value. And that means that this is an AMP structure relative to opposite value. So in other words, this is an OSO CMA structure. Now, that type of structure has some wonderful symmetries, and you can do, a lot with it, but it doesn't have the same degree of invariance relative to all of these shuffles that an OOO structure type has, okay? And that's what we get for an odd power of 2, okay? So let's look at, so maybe I'll go over here. So here is our Bessey sequence of length 32 that I kind of demonstrated, okay? So maybe I'll pop this up here somewhere out of the way. So why is this an OOO CMA structure? Well, it's because it is a two-cycle relative to opposite value. So here, what you do is you look at the first value in each half and ask the question, are these the same or different? They're different digits. That's a 1. This is a 0. That's a 0. That's a 1. And as you go down the line, you'll see that they are always of opposite value. The same thing for its mirrored structure. So when you come in from either end and look at the digits, they will always be of opposite value. As you come in all the way to the middle, there they are, a 1 and a 0, opposite value. Now in AMP, this is where you take them in pairs. Remember, we just kind of talked about that a moment ago. These will always be of opposite value as you move from left to right, okay? So that just shows you that for an odd power of 2, the CMA structure for such a sequence will always be an OOO. And it's that quality of the sequence that gives it the invariance that it possesses relative to all of these shuffles, okay? So I just wanted to kind of show you that and explain kind of what's going on there, okay? Okay, and so just to kind of summarize some of the things that we mentioned here, the smallest Bessey sequence is of length 2, okay? So this is like 2 to the first, and that 1 up there in the exponent is an odd number, right? But these sequences are just too short. This would be like having a red card and a black card. That's all you're doing. And so this will end up being a two-cycle relative to opposite colors. This is mirrored relative to opposite colors. And it's an AMP relative to opposite colors because guess what? There's only 2 digits there. Okay, but this is too small to be of any practical interest to anyone. So technically, you could put this little packet through all of those shuffles, and guess what? You either get this or you get its inversion. Big surprise there. Okay, now the next Bessey sequence takes us to sequences of length 8. Okay, and that's what our entire series has been focused on. This is what we've been calling a Bessey sequence of either length 8 or order 8, okay? Now, the next larger one, as I just tried to explain, is a Bessey sequence of length 32. And it has all of the shuffle invariance that the smaller Bessey sequences has, which is just amazing, actually. So I just wanted to point out that indeed there are Bessey sequences of higher orders or of longer lengths than 8. For a packet of cards, the only ones that are of practical interest would be of length 8, which is the one that we've been focusing on, or length 32, because the next Bessey sequence has length 128, and that's what's that? 3 decks. You're going to need 3 decks to accomplish that. So, okay. So I just wanted to kind of round things off. I wanted to put it out there that there are higher order Bessey sequences that can be taken advantage of. And there are just amazing, amazing things that you can do with this Bessey sequence of length 32, because it truly is fractal in nature. And so you can take, judicious parts of it and break it up into pieces where you know what the structure of each piece is, and you even know how you can mix those individual pieces and even recombine them again to once again achieve a Bessey sequence of length 32. And then you can divide it up as I did there. You can separate it into, let's say, reds and blacks, or whatever cards that you want to focus on in those special positions, because that's key, because that's what we were doing with the shorter ones, right? So the 0s and 1s are just really marking the location of where cards are going to be kind of grouped together at the end. Okay, so we know something about this position here, this one, and its relationship to the middle cards there. Okay, so it's similar for a Bessey sequence of order of length 32. Okay? So there's many ways to take advantage of the labeling here for zeros and ones, and you're free to have whatever you would like in the positions marked by ones and or the positions marked by zeros, and then put it through just tremendous mixing, and in the end be able to separate that packet in a way that will be completely inexplicable to virtually any observer. They'll have no idea how in the world could that be mixed in the way that you've mixed it, and yet you're able to separate the cards in ways that should not be possible given the, quote, randomization that they've just witnessed. Okay, well, thank you for watching, and I just wanted to make you aware that there are higher order Bessey sequences out there.